Okay. Everybody can hear me? Okay, let's get started. How many of you have my classes before? Okay. And you still here? This is an experimental design class, and it's not a pure statistic class, it's not a pure optimization class, it's experimental design class. What does that really mean? I'll use some toy problem to help you figure that out. And you can ask those who have my classes, what do you have before?
The summer class of...
Oh, the reliability?
Yeah.
Okay. I pretty much follow the same format. I always have a lot of toy problem, and then those toy problems turn into your homework, and you develop the template in order to solve bigger problems. Okay? And I don't like to prove or talk. I like, I give you something, you know there is a perfect answer. And if you don't get that answer, you know you're in trouble. Okay? And, right? And once in a while, I'll give you something open-ended, but if it's open-ended, I'll let you know it's open-ended. Okay? But generally speaking, to me, I follow the basic principle. If you take my class, you learn two things. Either you learn how to build toys, play toys, or you learn software, how to play software. So everything is data-driven. You need to prove your points by numbers. Okay? And what is experimental design? I upload the syllabus into the one module. So they're uploading the new one, but it's pretty simple. If you're a grad student, okay, the undergrad and grad follow pretty much the same things, and I'll explain their textbooks, but I never use books. And usually, I think my lecture notes, it's a lot easier to get to the point. So, if you got to read books, I'll give you a few books and tell you where I get most of my materials from. But if you guys have, intel to figure out some old test, what I did before, even NC State or somewhere else, go ahead, okay? Because I never really repeat myself. I usually just made up my problems. So, you need to think with me. And once you get it, it's yours, okay? Don't try to memorize anything, because there will be a set of logic for you to go through stuff, okay? And what else? Yeah, homework every week. When the homework usually do? Sunday midnight, okay? And don't say, oh, I have this problem. No, if you miss the homework deadline, you miss the homework deadline, okay? And the other thing is that usually the homework not too far away from the problem I did in the class. And probably first half of the semester, we use Excel. Okay? Before Excel, I used pencil paper. But now Excel is convenient because what you see is what you get. And so that's the benefit. Okay? The other things is that second half of the semester, we'll use SAS. Okay? SAS is a statistical package, operation research package, and the benefit is free. So you have it on campus, and you can use VPN, log on to SAS website. The SAS headquarters is in Raleigh, in Cary, not far from here. And I used to be faculty at NC State, so I work with them a lot, and it's a decent software, okay? And if you say that I would like to solve my problem using MATLAB or using R, fine, as long as you get to the answer, okay? And why no SAS at the beginning? Because SAS is very convenient. There's few commands, tons of output. So if you don't know what you're doing, you give you a first sense of security, like you actually done something. But if you use Excel at the beginning, you know step by step, you can visualize what's going on. And if you don't get those things, you know that you're not your mind is muddy. So you need to go through the steps. Once you understand everything's, and when you use SAS or abuse SAS, you have confidence, okay? And that's pretty much it. I think we probably have 3 exams, okay? And usually, well, if I think the exam time is going to be too long or something, we can arrange on weekend, just everybody show up, 4 hours torture. Or sometimes I can do this, over the weekend and say that this is a take-home exam. And I won't mind you guys even discuss what's going on, because at the end, you need to show your own stuff. And the other things is that if, it's a standard test, what I can do is when I give you the exam problem, there's some random number in there. So you will get the answer, but the procedure will be a little bit different. But if you copy-paste somebody else's answer, I have my lie detector to figure that out. Okay? So probably 3 exams. For grad students, no matter online or on-campus students, you will have a term projects. And why I'm so nice to undergrad without the term projects, because they have sophomore projects, 2110, junior projects, 3110, and then senior projects. And most likely, and I'm pretty confident about this, is that when you start doing your senior projects, you'll appreciate experimental design. Okay? What else? Yeah, I those jargon in the syllabus a little more later, because right now, if I throw a bunch of GRE 3 syllabus words to you, this sounds fancy, doesn't mean anything. So let's do an experiment. Okay, so the first experiment, imagine this, okay, where we're going to have build some paper airplane, okay? And what's your initial? Initial name?
GH, grade level.
Okay, GH. Okay, GH, design some airplane. And for the budget reason, I give you 4 pieces of paper, so you build 4 of them, okay? But only one condition. GH is a very decent company with good credit. So everything you build should be consistent, exactly the same, as much as possible. Agree? Okay, what's your name?
NE.
NE. And you're in the same case, you build 4 airplane. Okay?
TW.
TW, okay. Not TWA, huh? BM?
BM.
B, okay. Oh, BM, okay. So, there are 4 companies, okay? And do I have any priority or order, or I just have 4 companies? Right now, there's just 4 companies, right? So there's no company 1, company 2, company 3, company 4. There's no taller company, shorter company, rich company, poor company. There are 4 companies, okay? And now, first thing first, each one of the company got 4 pieces of papers to build an airplane. And build 4, build 4, build 4. And so totally 16 airplanes, right? Then I'm going to test their performance. And right now, just give me one performance measurement. What do you think is a good performance measurement?
Distance flown.
Okay, how far can you fly? Okay, so we're going to say that we're going to build airplane and measure the distance. Okay, so fly your 4, fly your 4. So 1, 2, 3, 4, 5, 6, 7, 8, all the way to 11, 12, well, 13 to 16. Okay? Agree? Wrong. Why?
Because you did it in a specific order.
And so she's gonna say it's not fair. Why did he fly first? Right? And then, of course, you can say, that's not fair. You know, why should I be beginning fly first? So the first thing first is randomization. Okay? In Excel, the randomization is called rand. Okay? So we'll put a random number down and pay special, lock the value. So here are the sequence we're going to decide based on those random number. Okay? So the first thing is rank. Hey, what's this number? Rank among the 16 number. Okay? So when we're done, we have the experimental sequence. And just double check, you know, the max and the mean. Okay? Let's just do a sum. It shouldn't happen that for such a small experiment, you know what I'm worried about? There are two numbers exactly the same, then that'll be a problem. But here, you don't see any duplication, right? The rank is okay. Okay? What's the beauty of this? Generally speaking, okay? The average rank okay. Not too good, not too bad, but, you know, it's kind of even out. Okay? So, do you think the game is fair now? Okay. So let's pretend it's fair. Because nothing is really fair. Okay? Okay, here is the experimental sequence. So next, we'll start putting the number down. Okay, GH, you're number one fly. So GH, give me a distance. Imagine a distance for me. 10 feet? Okay, so let's just say 10.3. I give you extra credit. Oh, 10.4. Even better. Okay, and TW is number two. And what do you think?
12 feet.
12 feet? Ah, greedy. I don't like it. Okay, so if I'm doing this, what will happen? Sooner or later, trial 1, trial 2, trial 3, trial 4, I'll have all 16 number done. Agree? So let me fake that 16 number. Okay. Okay. Control C, pay special, value. Okay. So, first thing first, just by looking at it, which one is the better one? Based on the distance. Hard to tell, right? But we probably can do a sum, right? The total distance, or divided by 4, get the okay. So which one is the champion? TW is the champion. How many of you agree on that? Show hands, don't be shy. Okay, how many of you will bet your life on it, TW is the champion? You know, when I said bet your life on it, in a legal jargon, it will be beyond reasonable doubt. How many of you think that's the champion? Not sure, right? Not comfortable with. So let me put a little bit of juice there. See if you like that better. Okay, so oh well. Okay, now 84.5 is the distance of TW. Good? Would you like to bet your life on it? Ah, chicken. But how many of you think that if I give you $1 million to invest, you feel comfortable to invest among the 4 to TW? Yeah, so obviously there's something in those numbers that make you feel like it's beyond reasonable doubt to do that. But where that beyond reasonable doubt coming from mathematically? That's pretty much the essence of this class. Okay? And of course, let's play a different tricks. Okay? Okay? And now, let's just say that GH is short. Okay? GH should be kicked out of the market. Okay? Okay, but how much you think GH is bad? VM is not too good either, right? So is GH as bad as VM? So in other words, is that if this is a compact, this is VAX, they're all big companies, pretty good in the mini computers, you know, but those building up 20 years ago. So are they equally bad, or this one is worse? Again, right? Is it beyond reasonable doubt to say how good is good enough, how bad is bad enough? So let me just make this okay. Pay special. Okay. Now let me start approaching this through the beyond reasonable doubt. Okay, the analogy I'm going to use is the following. Okay, how many of you have ever been to New York City? Okay, for those international students from India? Okay, Mumbai? Yes. Okay, so you have a nice train station, right? Victorian nice station. Yes. Okay, and there are subway coming in. Yes. From different part. Okay, if you live right next to the central station, would you use the subway? Probably not, because you can just walk there. So same things, if you live in Manhattan, you're close to the central station, you're not going to use the central station. So the things what we're trying to say here is that if you are too close to the central station, okay, there's no difference. So when you're going to use the subway is that you know that, hey, let me walk or commute to the subway, the nearest subway, I can take advantage of the subway, use the subway to the central station. So first let's figure out where's my central station. So here is a set of number, okay? Some good, some bad. Okay, so let's just, okay, so I'm going to put a number here. Here is the order of experimentation. Okay, and now, of course, this is the observation. Okay, so now we need to figure out where's the central station. So what is the central station location? The central station location, the center. Central station. Okay, the central station is the core, it's the frame of reference of everything. So it's what? The average of the 16 number. Oh. What did I do wrong? Oh. Okay, so the location of every observation is how far away from 17.6. Obviously, TW got a lot of them above 17.6. And the other one is a little below 17.6. So the differences between the two, we can say that, hey, customer 1, customer 2, customer 3, or test run 1, test run 2, how far are you away from the center? 5.8 below, 0.2 right next to it, I'm 10.2 above. And then we can call this sum of square of every observation together. 382.8. This 382.8 is called total sum of square. Hey, you don't stop me, I fly, okay? So, okay? So this is the total sum of square. Next. The problem is, I'm living this far away, below, above, okay? But I'm not driving there, I'm not walking there. I would like to take advantage of the GH design, NE design, TW design, VM design. So in other words, what? Commute to the train station and then use the train, right? So I need to know where is the train station. So the train station is the following. Is the average distance of this. Okay? Okay, people, first thing first. Why are those phone numbers the same? Avoiding eye contact? Why? Because they're from the same company, they have the same design, they are the same subway station, right? If you want to use subway station GH, you're going to commute 14.4, right? Agree? So, if, okay, that's my location, and then I'll use this minus this. What are those things mean? Hey, this subway station is negative 3.3 below the center station. No matter for this flight, for the first flight, second flight, no matter for which flight, as long as you're flying out of that, or as long as you're getting out of the, your commute started from GH, you're gonna have GH below, going up to the center station. If you're from TW, you will be 3.5 above and coming down. Agree? Show of hands. How many of you feel like I'm talking in Martian? Okay. So we'll have another sum of square. This sum of square is called total sum. This is called total sum of square. So this one is called Treatment sum of square, or sum of square of treatment. Treatment sum of square. Okay, the treatment sum of square, if you do a sum square, okay, it's 93.87. Okay, next, okay, for every commuter, is this only the distance they need to travel? 3.3 from below, 3.5 from above. Every commuter, are they live right in the subway station or they live somewhere else? If they live somewhere else, they need to use the subway station. They need to what? First travel from their home to the subway station and then to the central station. Agree? Right? That commute is the same no matter you live in Mumbai, Tokyo, or New York. Right? Well, except in Charlotte, we don't have downtown, we have uptown. Okay, so we do that. So this is the subway station. Okay, so finally, let's measure how far the travel I need from, let me write it over here. Okay, how far is my travel from where I am minus where is the subway station? Okay, so now if you do another sum of square, of all the local commute is 288 point this. Now, here is the things. Anybody figure out what's the relationship among the three numbers? I have three numbers. One number is the total sum of square. One number is total, the treatment sum of square, or where the subway station is. And then, let me just write it down. It's called arrow sum of square. Okay, what you can do is this, okay? If you use this number plus this number, guess what you're going to get? Okay, Okay, so that's the things, I don't want you to just memorize it. I want you to, I'll give you 30 seconds to think about it. What I just proved is Pythagorean theorem in statistics. Right? Every commune, if it's in, what's Pythagorean theorem? A squared plus b squared equals c squared. And a c squared is my total commune equal to my local commune plus my subcommune. When I up them up together, that's the answer. So Pythagorean theorem, you can do it the other way around, right? A squared equals c squared minus b squared. Right? So now I'm not supposed to get that close to you without my mask. But see what's going on? Do you think this is only good for this set of data? Okay? Now, first, I can make this problem, well, at the end, I can spin any way I like, and you should be able to spin any way you like. Okay? If I shut it down, can you do it yourself? Huh? No? Then think a little bit. Okay, don't look at the screen. Okay, let's do this. Step one. What's step one? Huh? Generate a random number for what? Exponential sequence, right? And why do we care about exponential sequence?
So now that it's as fair as it can be. So it's as fair as it can be.
Yeah, fairness. Yeah. So everybody will say that, hey, it's my luck, so I stuck in this sequence, right? Okay, and everybody said, we agree with the sequence, just like Olympic, right? I'm in lane 4, I'm in lane 7. Why? Because the random numbers are so. Okay, once we have the sequence generated, we start in what? Observation, collecting data. Now, right now, they said they want max, so I do max. Later we can do something else. Okay, it doesn't really matter. So, you observe the data. Once you observe the data, you start thinking about what? Here are 16 numbers all over the place. Right? And what's in your head? Well, if this 4 number is from the same subway station, from the same company, they should perform equally good or equally bad relative to the central station. If you're bumping all over the place, that's not trustworthy. So you should be what? About the same, very high or very low. Agree? So in order to prove that, we need to come up with 3 different numbers. Well, this is Simon Chung's target, okay? No textbook says subway station, but I feel it's easy for you to think about it. So every commune becomes what? How far away from central station can be partitioned into how many parts? 2, right? What are those 2 parts? First, from your home to the subway station, and then from the subway station to the central station. So you start looking at a number, you say that, okay, how far each one of them away from the central station, and how do you figure out the central station? The overall average, right? You have the overall average, you have the central station. And then how far away from that get the, so one way we can visualize this is by doing this. Insert shape. Where's shape? Can't find it. What is this? Okay. So you can imagine this. All the observation we'll consider as the following. First, there is a central station location, and then there are a bunch of local station, and then the travel distance using that is going to be exactly the same. So in other words is that if I'm commuting from this subway station this is the distance I have to travel if I use that subway station. And if I'm using this subway station, while you're looking at my animation, you think about the, let me do it this way. The Excel on the other side. Okay, I just want you to see that I'm doing exactly the same things. Not like I'm doing anything fancy. Would you agree? The travel is the same. Okay? If I'm going to the subway station, the travel is the same. And then, remember, for each one of them, they're not living in the subway station, they live somewhere else. So there are some randomness going on. Okay, I need to come from here to the subway station. I need to come, I live a little above the station, I live a little below the station, I live very, very far away from the station. So everybody needs to travel a little bit more. Is that a little bit more? No time to use different color, wasting time. So, can you see that PowerPoint relate to what I just did in Excel? Okay? And it's important, okay? I don't want you just kind of, yeah, you prove that two numbers add together equal to the third number. What's the representation of the data? What's the meaning in this experiment? You need to think about it, okay? And then usually, how far away from the overall frame of reference. That's called total sum of square, okay? And then there are sum of square due to the, where my treatment is going to be, or where my subway station. That is called total sum of square of treatment. And then there are local commute, a little higher, and that's the total randomness. That's the error part. So total sum of square equal to total sum of square, equal to sum of square treatment plus sum of square error term. Okay? Okay. Who is the most quiet one? and avoiding. Yeah, we sit in the back. Tell me, which number you think should be big to make some sense?
Should be big. The last one that you got.
Okay, there are three numbers. Total, treatment, error. Which one do you think big is good?
For total,
Total is big, but total could be big due to the local commune or the subway commune. Which one you want to do? Treatment or error? Here, let me ask you this. What was the question I asked them? If you live right next to the Mumbai Central Station, would you take the subway? You know, you're just having fun, right? It squeezes all the way out and then coming back. Right? No. The only time you will use the subway is what? You're living far away from the central station. So, in other words, is that this three number, remember this, okay? If I, here, let me show you. Okay. If, okay? Let me just copy paste everything. I don't want to copy everything. Let me find a way to. Okay. Can someone copy down those three numbers, 382, 93, and 288? I'll do it myself. I don't trust you guys. Okay. Phase special value. Okay, so this is the original design, okay? Look at this experiment versus this experiment, equal to this guy's plus 100. Okay. Phase special value. Okay, yeah. Doesn't make any difference because I'm using the same things. See what I did? I just said that, hey, add 100 to every observation. And does that change any of the sum of square? It doesn't. Why? Because I can call my central station 1 billion, or I call my central station 100. But the relative distance didn't change, right? So what we're really doing is what? It's to make the subway station far away from the central station, but the central station maintains the same. So let me try a different way. Okay, so this time, if, okay, what should I do? What should I do? Okay, so I'll have the big one even bigger. Okay, so let me do this. Minus 5 is equal to this one plus 10. Okay, and Control C, paste special value, Control C, piece special value. Okay, now, people, look at this. This is the original sum of square. So this two number equal to this, add together equal to this number. This two number add together equal to this number. But what's the difference? In the original sum of square, okay? The treatment divided by this is 24% or 25%. And the error, the local commute over the total distance is 75%. So in other words is what? Every flight or every commuter spends 75% of their distance in their own commute, in their own car. Only 25% take advantage of the public subway. That's not a very good subway, right? You know, if I'm driving 75, I probably would have said, man, I'm going to drive all the way to downtown. Why bother to use the subway? However, if you look at this one, okay, what's the percentage of the subway commute versus the total commute? 77%, right? I reverse the sequence, and the local commute is what? 22%. Okay? So, city A versus city B. Which city do you think people would like to use the subway system more? Huh?
City A.
A, right? Why A? Because I drive a little, but I can take advantage 77%. If I do it here, it's dumb. Because, you know, I always put in so much of my personal effort, I can only take advantage of the treatment tiny bit. Okay? So, what's experimental design really trying to tell us? Beyond reasonable doubt, right? So we're going to say that, hey, are you designing something beyond reasonable doubt for people to say that, I like the treatment, no matter for big or for small, because at least I know that if I'm using this, I'll get some advantage. Okay? Give you 30 seconds to digest a little bit or ask questions. This will be your homework one, okay? Due on Sunday. You know, I probably was not using 4 number. Well, what can we do 5, 5? 25 observation and do the same thing. And again, you know if you got it right or you got it wrong. Okay? And of course, later on, I'm going to say that this comparison. Anybody know what's the name of this sum of square table called? Anybody heard of ANOVA table before? Analysis of variance? Okay, that's okay. Give you a little bit of reading material. Just go to Wikipedia, read ANOVA. Okay. It's called analysis of variance. Okay. And let me. That's good enough for you to listen to all the jargons. And while you're listening to the jargons, or get familiar with the jargons, have you seen any equation looks familiar? Right on there. SS total equal to SS error plus SS trimming, right? I didn't ask you to memorize it. I want you to play with it and see it yourself. Okay. And same things, okay? I know you guys probably learned statistics using the table in the back of your book, right? I don't like that. I'll teach you how to generate those tables freely. Okay? If you have to trust on something you don't even know where it's coming from, you shouldn't trust it. Okay, so, yeah. Wikipedia gives you some jargon, and every jargon they talk about, I will find a Excel to help you get used to it. Okay. And I still have time. So, when we generate this table, okay, obviously people will say, hey, this got more treatment effect than this. Hey, this is 77%, this is 25%. But Simon says that it's beyond reasonable doubt. So what is the reasonable doubt benchmark, yardstick coming from? Right? So we need to figure out a yardstick, or our z table, our chi-square table, our f table. Okay? And yeah, I have time, so I'll do it. How many of you heard the term central limit theorem? Never heard central limit theorem? Did you take your stat? Come on. I'm not going to put you. How many of you ever heard CLT, central limit theorem before? Okay. What does that mean? Yeah. Anyway, you want to give a shot?
So, area under the normal distribution curve is 1. This stated by
Central limit theorem is the power of average. Okay? Or the power of sum. So, let me do this. Okay, so consider this. I have one 10,000 random number. Okay? And if I use this 10,000 random number, pays special value. Oh, by the way, okay, if you have any things along the thinking process you didn't visualize, you need to discuss with people and catch up. Because I don't give you something kind of like, you just memorize it for homework 2, not going to get used. Everything that I cover at the end, they're all part of a very, very well-defined structure. So, don't allow yourself to have missing link. Okay, so if we have this 10,000 random number, could be any random number, okay, from any distribution, doesn't matter. And then if you do a data analysis, let me do this first. We don't have time. Just do this. Go to data analysis and look at histogram. Say, hey, I would like to have a histogram, and without setting up the beam. Okay. Once you do that, you will see that a random number. I have some, number I didn't fully evaluate because it doesn't matter right now. But generally speaking, See, the random number is from 0 to 1. Everything is possible, right? It's random enough, right? And since this is a uniform, so it looks uniform. However, if I generate a bunch of random number to oops. Okay, so now I have a lot of random number rather than just one. And then I say that, hey, I don't care this random number or this random number. I care about what? The average of those. So I'll take the average. Of this random number. And now, rather than figure out a histogram of those random number, I'm trying to figure out a histogram of the average of the random number. So if you go to data analysis, histogram, and then you just say that, give me the histogram of those average random number. Okay? And when you're done, and look at the chart, what do you see? Do you still see a wiggly things? Or you see something different? You see the bow shape, right? So what is central limit theorem? Central limit theorem is the power of average. If you have a bunch of random number, I don't care where you get it from, as long as you get it from a random number generator. Once you take the average, the power of average will do what? Fluids, turn them into a nice looking bow shape. Okay? So central limit theorem basically is what? If you out for job interview, people say, hey, you have stat before. What's central limit theorem? What should be your answer? The power of average. Because once you have the power of average, what's the beauty of this? You only need 6 sigma, right? Majority of the number in the middle. To get really big or to get very small, getting what? Less and less light. Right? So we're going to use this to build z-score. And once we have a z-score, we can square it. We get our chi-square distribution. If we have our chi-square over chi-square, we have our f-test. And then you look at your step 101 in the back of the book. What? Normal distribution, standard normal distribution, chi-square f distribution. You don't need this. You can do it yourself. Okay? So now when we say that we want to say our subway station commute is finally. If we want to say that our subway station commute is really significantly different, beyond reasonable doubt different, we compare them with what? Some randomness. If this is so far different from those pure accident, then we know that your design probably means something. Okay? So, this will be your homework too. first generate a bell shape, and then I'll show you how to turn them into chi-square and f-test, and then how we compare that with our observation. Okay? I think day one torture is enough. Okay, let's talk about your syllabus. Okay, Montgomery, yeah?
Oh, I just had a question. Are you going to make our Canvas module available so that we
Yeah.
Okay.
Yeah, probably it's already available right now. Just still not? Go to the combined module. There is a 4141, 5141 online on campus or in one module. Should be in there. Okay, and then if I record it, I'm recording the videotape right now. The audio and video and whatever I did on the screen will be there. So I know some of my ex-students tend to do this. Sometimes they just ignore my lecture. They just find where I did something. They just zoom and see, oh, C7 plus A2, and then just copy paste and try to get the same number. But that's not good. The first step is you can copy what I did, but the second time you should be what? Think it through yourself, okay? Okay. Let me summarize what I covered in the last hour.
So we have 4 companies that you gave them 4 pieces of paper, and so them that you have to make airplanes, and you wanted to have 4 airplanes made consistently as possible. So then we randomized.
We want them to be fly as far as possible and consistently as far as possible.
Right.
So I'm not just accidentally one time really good. If I'm good, I'm always good. My 4 is always better than any 4 from other company. Okay, keep going.
And we made a sequence where the order was in fairness with everybody. So it wasn't just a hand-picked 1, 2, 3, 4. It was just randomized. And then based on that, we ran the test and got different values for the distances. And then based on those distances, we compared it to like the central system. And then we got the difference with that, and then we compared it to where the subway stations would be relative to the central. So we made that.
Okay, using that analogy, you want the subway coming wrong or you want a local coming wrong?
The subway would be wrong.
Because subway is supposed to be the treatment. Yeah.
And then at the end, we pretty much use the Pythagorean Theorem out of the last 2 error values to get to the first one. And then we compared city A, city B to see which one would be more useful to use the subway train.
Very good. Very good. Everybody agree with me? Yeah. Everybody want to say that I can say it better? Okay. Now, these books, there are several different versions. You know, if you can find some cheaper version, 2016, 2015, that's fine, I don't care. Okay, it's just, this is the popular one. Okay, and I'm pretty much, this is like how I teach reliability, right? Yeah, so just now we're face to face. First step, you can do the same thing, think it through. Second step is get rid of copy paste, start thinking about, you know, Why someone does this, why someone does this, what's the rationale, okay? Nothing gonna get waste. So you learn the following: compute, interpret the data sample mean and standard deviation. Okay? Establish a statistical distribution. Did we just do a histogram look like bell shape? Okay. Construct and interpret a confidence interval. Are we very, very close to the center, or we're far, far at the tail? Fit a model using method for maximum likelihood or least square. We're not there yet. And testing a hypothesis like t-test or whatever. Okay? In the exam, I don't want you to memorize anything. I want you to visualize things. Okay? So, just like central limit theorem, we can memorize, but at the end you still say it wrong because it's not in your system. Okay, so DOE is a basic course in designing and analyzing data. All experiments conducted by engineers, scientists, okay, are designed. Okay, a well-designed experiment can allow one to obtain the desired outcome. What's the desired outcome for our airplane? As far as possible. And later, we could be as small as possible, as close to a value of standard as possible. Okay? And to be more efficiently and effectively. This is a good engineering management student. You heard those two terms before? Efficiency, effectiveness? Never? Yeah. Enlightenment. What's efficiency? What's effectiveness? Efficiency is do things efficient. What? Huh? No, what is effectiveness? It's got nothing to do with performance. Really? Okay, so what's the difference?
Efficiency, once we complete the task as least step as possible, but effectiveness wants the product to be in its best state.
Okay. Effectiveness is about sense of directions. Does that way get big or does that way get big? Should I go that way or should I go that way? Efficiency is how to get to that big answer as quick as possible. Okay, so one is related to sense of direction. One is related to the procedural. Okay, so which one is related to the sense of direction? Effectiveness, right? Some people, they're very, very efficient. But they're efficient in the wrong way. So at the end, they didn't, they produce a lot. They produce a lot of useless stuff. Effectiveness is what? I'm in the right directions. I get the good stuff, and I can get the good stuff as quick as possible, as cheap as possible. Okay? So DOE at the end is engineering management. Okay? And as such, we can reduce the developmental lead time for a new process and new product, improve performance of manufacturing process and products that have superior function and reliability. Okay. Still sounds like jargon, but a little better now, right? Yeah. And we'll do estimation of the variation. The estimation of variation really just the sum of squared divided by the degrees of freedom. I'll explain that later. And then we'll start from single factorial, and then 2 factorial, 3 factorial, and then the multifactorial really is just combo of those. Okay, we'll talk about mean comparison. What's mean comparison? Subway station comparison. And we'll have block design. We'll build contrast. We'll do factorial design. And then we'll talk about Papucci, explicit plot, and response surface, and hope you learn some nonlinear optimization. Okay? That's why I said, if you do this right, can you visualize this be used in your senior design? Yeah. Yeah, I don't want to teach you something you cannot use. Okay. So. If you cheat, don't get caught. If you get caught, I'll kick you out of the class. Okay? No bargain, nothing. And don't worry, I'm not gonna, scare you or walk behind you. Can you tell? I know some of the numerical tricks. I can catch you my own way. Okay? A little background of myself. Before I become professor, well, I was endowed at Texas Tech and I was tenured at NC State. Before I joined academia, I worked in the industry. I worked for Liberty Mutual, the insurance company. So I'm good in developing a lie detector. Okay? And before that, I worked for United Airlines. So, how to operate the friendly sky. Without me, not so friendly. Well, anyway, we record it as a joke. It's a joke. But anyway, when you write, don't copy paste. Okay? I don't care, let's discuss. But at the end should be my stuff, my way of thinking. Okay? And for the disability service, whatever reasons, give me the letter. Okay, I'll find a way to accommodate you. And in the past, we have students say, I would rather doing the exam through their process, but then they realize there's no difference. Because what will be my exam style? Open book, open notes, open everything. And why? Because I don't believe we can copy paste from or Google the answer anyway. Yeah, I can make up stuff, and if you don't know what's going on, you probably waste more time trying to Google the answer. Okay, and for the grad student, your term projects, we'll talk about it later. Okay. After we have enough material so you know what kind of experiment is possible. Okay? Okay, adios. Have a good one.